Thank you. First of all, let me thank Professor Ganser for the very nice invitation and for the nice efforts for this beautiful and nice conference. It's quite pity, as I said, that I could not attend the conference locally because the pandemic control in China. Turkey is a beautiful country and very, very pleasant and friendly. So I really want to visit Turkey many times. Okay. So today I want to give the talk about a strong local pairing, interplay between superconductivity and antiferromagnetism in corporate superconductors. It sounds a very old story, but I will show new data. 3 pieces of new work coming out from my group in Nanjing University. My name is Hu Wen, so you can see the photos of the young brilliant student in the group and my young colleague Huang Yang. So the work many experimentally done in the group and also samples from several other places. I will mention these collaborators later, okay? So we know that cuprate was found in 1986 and in 1988, very quickly the Nobel Prize was issued to Benoist and Miller. And the typical structure for the cuprate is this carboxygen plan. Okay, we know that this is the major player for cuprate for superconductivity, and between them it is a charged reservoir layer. Okay, actually after so many years study, nowadays I probably can conclude for some consensus yet. Now, for example, the parent phase is an antiferromagnetic multi-insulator. And the electron conduction and the superconductivity arise from doping a multi-insulator. And I personally believe that the D-wave pairing has been proved, which reflect the repulsive induced pairing. So it must be most likely the magnetic origin. Otherwise, we cannot get this repulsive induced pairing. Okay. Can you see my mouse here on the screen? It's moving. Chair. Okay, so this is a generic phase diagram for the cuprate superconductors. We know that starting from this parent phase is the undoped parent phase, which is antiferromagnetic order, and gradually superconductivity comes in. Okay, so this is, and on the t=0 state, you can see a lot of competing orders. So there are many competing orders. These orders compete or coexist with the superconductivity. However, many questions remains unclear. For example, how is the Mott-Nash related gap filled up together with the vanishing of the long-range antiferromagnetic order? And how do the low energy density state accumulate near EF, the Fermi energy? This is very important, the second part, because in the correlated system, we don't know how the low energy density state accumulate. We need some direct data, direct evidence for that, okay? And also whether the local pairing, Cooper pairing really exists and in what form, and whether the antiferromagnetic order can re-emerge in the superconducting state, okay, if it's a competing state order, okay? And how far is the normal state from the Fermi liquid picture? So this is some very important topic I want to address today through our data, okay? So my talk is outlined as the following: 3 pieces of recent work. One, I will show you a so-called local pairing through a very interesting confined pneumatic state within the basic 4A by 4A plaquettes in extremely underdoped BISCO 2201. The second part, I will show you direct visualization of a re-emergent static incommensurate F order, even in the optimally doped BISCO 2212, which indeed shows that the antiferromagnetic order comes out with the gap intact. Okay, so the superconducting parent gap are still there. And then finally show you another piece. Third piece is about the Plancking dissipation in the normal state. And also want to show you the so-called Ginsburg-Landau type apocritic field in this optimally doped BISCO 2201. And finally, I give some concluding remarks, okay? So this is the phase diagram for the BISCO 2201 showing here. This is a crystal structure, okay? So you can see that up to about 10% doping, always the people draw the phase diagram that it is anti-Fermi order. But besides some neutron data, shows some trace that actually is not clear. We don't have direct evidence for the so-called anti-Fermi order. I will show the direct evidence today. And also in the neighbor, it is a superconducting dome. And the boundary locates at about 10% doping. Okay, so here we take two special doped sample. One is 8 doping, one is 10% doping. So you can see we measure the resistivity of the sample single crystal. So this 8% doping shows a very huge and strong insulating behavior. And the 10% doping, the resistivity becomes much lower, but however, still shows a semiconducting behavior. Okay, and please remember that the superconductivity just appear at the boundary of the 10%. Okay. About the parent phase and the underdoped side, actually in the cuprate nowadays, we know that it is due to strong correlation. And the correlation, this so-called correlation gap, U, is quite large. However, in the cuprate, we know that this lower half of the band and the oxygen band are hybridized. So in that case, we have so-called charge transfer gap, which is also Montanus derivative gap. Okay. And the early picture about superconductivity, it was very strict and very interesting, says that the parent phase is due to this kind of spin liquid, and each spin singlet is just a Cooper pair. When you dope holes, this singlet will move, they will behave like superconductor. However, later experiments show that the parent phase is anti-Fermi order, and the evidence for this RVB state is still lacking. Okay, so this picture may not be completely correct. Okay, however, we can still get some feeling that the parent phase is a multi-insulator, and the local superexchange J produced by this correlation leads to the anti-Fermi state. So this theoretically can get the precise solution. And the superconductivity emerges when some effective density state appear near the Fermi energy. But how the effective density state appear in the correlated system, that's a question and a big problem, okay? And how do the charges move on this doped multi-insulator? There are many models. As I said, the first, for example, the so-called Zhang-Ran singlet based on the Hubbard model. So the holes are doped to the oxygen side, and they will form a singlet with the nearby spin of copper. Okay, that one move lead to the conduction, and also yes, and also the quasi-particle, like the so-called coherent quasi-particle based on TJ model by Hu Wen and Patrick Lee proposed, and also through phase separation and stripe phase proposed by Emery and Kieferson and Itel. Okay, and also very interestingly, based on the RVB picture, Professor Zheng Yu Wang in Tsinghua University proposed that it could be form this kind of phase string effect that leads to the pairing and the charge moving. Okay, and also model by Professor Wei Ku et al. Just generally they call the charges in the normal state as the bosons, which is called a bosonic liquid. So there are many models. Okay. So first, let me show you the data, the transport data for this 10% doping, supposed to be at the boundary. So you can see that this single crystal, if we measure resistivity, when the current is large, then we see a huge insulating behavior. Okay. However, when we lower down the current, then the superconductivity somehow sets in. Also, the transition is not complete. Okay. And for some samples, we don't see, even with the smallest current, we don't see this transition. If we blow up, take the sample 2, blow up the transition part with a different current, you can see that even for this sample, with a very small current, we see the superconducting transition. Okay, and this transition seems to can be suppressed by the current and also by magnetic field. You can see that. So with a small current, you can see superconducting transition. However, when you apply a field, then transition gradually smooth out. So even for this so-called sample on the boundary, supposed to be a non-superconducting sample, but actually when the measuring current is small, then you see superconducting transition. So this is not a matter of the sample quality. They are single crystal samples. It is the intrinsic property of the sample at this doping level. It says that we have a fragile and superconductivity on top of a strong correlation background, okay, even for this sample on the doping level. Then we use the spin polarized STM to measure whether we can see the so-called anti-Feynman order. So we thank to Professor Wissendanger to help us and give some advice for us to build up this STM with the spin polarized ability. And we published some papers based on that kind of study. So we first characterize the spin tip with so-called ion tellurium. And this sample, you know that it is antiferromagnetic, okay, which has a so-called bicollineal antiferromagnetic. So we measure spin up and spin down topography with subtract. Then we see this kind of bicollineal structure. Let me move here. And by doing the Fourier transform, you can clearly see this spot. This is due to the typical bicollineal antiferromagnetic order in the ion tellurium. So that's a check to the tip. And then we measure on this so-called 8% doping and 10% doping. You can see we use a spin down and a spin up to measure this topography. We subtract. Then we can see this kind of a blue and red, which shows the intensity of this subtraction. You can see that it is the anti-Feynman order clearly visualized by the spin polarized data. Doing Fourier transform, you can clearly see that the anti-Feynman order. So I must say that this is the first time, very first time, to directly visualize the anti-Feynman order in the cuprate. Okay, and for the 10% doping, then you don't. We also measure spin down, spin up. Then we subtract. We don't see such order. After Fourier transform, we also don't see the spots. So that means that the anti-Feynman order exists at 8% doping sample, but on 10% doping sample, it does not exist. Then we take the 8% doping sample, we measure tunneling spectrum from the area with anti-Feynman order to the area without. Then you can see that the tunneling spectrum change from a so-called charge transfer gap region. So the gap is about 1.5 milli EV, okay, 1.5 EV, which is almost featureless in the region with anti-Feynman order. However, when you move into the region without this anti-Feynman order, then you will see that some kind of density state piles up in a very wide energy area. And the Fermi surface, Fermi energy is pinned here, okay? So you can see this kind of hump. This is due to the density state, quasi-particle density state through the doping. If we use this line as a subtract all the curves, okay, as a background to subtract all the curves, then you will see that once you go to the region without anti-Feynman order, you see this kind of density state piling up in this charge transfer gap, okay, and which forming a so-called large pseudo gap with energy about 200 milli eV. There is a hump here, okay, so this is a quasi-particle doped into the anti-Feynman order in the model gap, charge transfer gap to form this kind of density state. It is quite interesting to mention that actually in these iridates, Alain Milan's group also measured tunneling spectrum. They also see this kind of large pseudo gap. So for the strong correlated system, it seems they are behaving in a very similar way. And for the 10% doping, then we found that actually in the real space on the density state mapping, you can see a lot of blocks, okay, this kind of little blocks with the 3 bars inside, okay, 3 density state bars inside. We do the Fourier transform, then we see 2 scattering spots. One is 1/4, okay, another one is 3/4, okay. This one means that we have this 4A by 4A block, okay. And this one corresponds to the 3 bars within each block. So if we measure the tunneling spectrum, from outside of the block to inside the block, outside the block, it shows some kind of featureness. Inside the block, you see this density state again, okay, this density state by subtracting the background, okay. Let me continue. So then we pay attention to this particular block of the 4A by 4A, and we figure out the atoms of the couple and oxygen. Okay, and in that case, you can see that this tunneling spectrum. If we measure on the boundary, we don't have this low energy density state. We see a large V-shaped gap without a low energy density state. However, if we move into the block, let's say on the central bar, then we see that a low energy density state comes out clearly and with a small gap. And this gap is about 20 millieV. This mapping was measured on 20 millieV. So it seems that this very unique block 4A by 4A is very important. And it shows this kind of internal pneumatic state of a density state, low energy density state, okay? That shows some kind of small gap, which looks like the superconducting gap, okay? Then we make a cut, a crossing, this central bar. Then you will see that actually on the oxygen side, we see some kind of peak and knees, which means that the whole doped induced density state has some kind of maximum or knees near the oxygen, which strongly suggests that the holes are really doped to the oxygen side. So our data directly prove that the doped holes are really going into the oxygen orbitals, many on the central oxygen 2 and oxygen 3, as pointed out by Emery and Zhang Rice in the early studies, okay? So in that case, we plot this cartoon picture within this 4A by 4A, and we have the density state of this kind of parallel bars. This density state is high and forming a small gap, which is nearby the Fermi energy, which is very important, we think, for the pairing, okay? So this slide shows the control experiment to prove that the holes are doped to the central oxygen side. So you can see these peaks appear on the oxygen 2, oxygen 3, okay? So this as a control experiment. So we have measured for such. And to count the whole number, suppose that we have 2 holes on 1 plaquette, then for this 10% doping, we expect about 313 plaquettes, okay? This kind of pneumatic 4A by 4A plaquette. And we did the analysis, we found that the total number is about 297, so which is 0.019, 9.5% doping, which is close to the nominal doping. So this slide shows that we probably have 2 holes are doped to 1 block that form a pair, and that to form this kind of 4A by 4A, a very unique structure. Okay, so that's a basic pairing element. And for our 4A by 4A structure with internal pneumatic structure, one of the probability it is due to the pairing density wave, okay? And that one gives the low energy gap. About the pairing density waves, there are a lot of studies from Seamus Davis group and from Yao Wang's group, okay? So either 4A or 8A, some measurement, okay? And also even in the superconducting sample for this CCOC, you can see that for the superconducting sample, Hanaguri-san and in Seamus Davis group by that time also see this kind of 4A by 4A plaquette. And within that, they also see this 3/4, okay? And if the blow up, you can also see some kind of 3 bars of density state that's corresponding to this 3/4. So for that data, we can conclude that the 4A by 4A checkboard is quite universal, even in the very underdoped sample, but that one is not due to the quasi-particle interference. And we see this very unidirectional 3 bars of density state within the block, even for the superconducting sample. And also for other samples with a different area, you can see this big hump, pseudo gap, large pseudo gap, and the low energy gap. And the data looks very similar like ours. Even our sample is not superconducting and a very similar energy. So in that case, so the second probability for the small energy, small density, the density state at a low energy under the gap is due to the precursor gap for superconductivity. Okay, so in that case, here I show you 3 pieces of work. This one on BISCO 2201, and this is also in this optimally doped last time BISCO 2201, and this is overdoped in this paper by Professor Hu Wen's group, first time to mention about this so-called 3 unidirectional bars from the self-correlation. Okay, so our key discovery is on the boundary phase of conductivity, we found this kind of a pattern, which has a 4A by 4A. Within each plaquette, we have the 3 unidirectional density bars. And on these bars, we see this density state and a small gap, which mimics that of superconductivity. We think that it is coming either from the consequence of the pair density wave or the local pairing, the precursor pairing. Okay, so this is the first piece of work. This is about why it is a pneumatic within the block. We can find several literatures. Here I mentioned first one to you. So the Emery in the early days says that the holes may be doped to the oxygen state, and the pairing is mediated by strong local pair, strong coupling to the local spin configuration. And our data somehow is quite consistent with this one. But of course, there are other theoretical papers to show that in the underdoped side, it is easy to form this kind of a pneumatic state. Okay. So then I come to the second piece of work. So second piece of work is optimal doped BISCO 2212 with ion doping. Using ion doping, 3% ion doping, we suppress the TC to about 65K. Here shows the resistivity. And by using the magnetization data, using the Curie-Weiss fitting, we found that the ion yields a magnetic property. And because the tunneling on the ion impurity, it shows this kind of tunneling spectrum. So we can use a high energy tunneling spectrum to find the ion spots here. And on the ion spot, we see that the gapped feature on the tunneling spectrum is still there. But far away, then you can see that it becomes a normal superconducting curve. Okay, so this is on the ion impurity doped BISCO 2212. And here shows the contrast for the tunneling spectrum measured far away from the ion impurity, which shows a typical D-wave superconducting tunneling spectrum. But on the ion, you can see that the coherence peak is strongly suppressed, with the gap, however, intact, which again shows a strong local pairing. Okay, so here I also compare to nickel and the zinc doping. The ion doping somehow only suppress the phase coherence, the coherence peak, but does not change the gap too much. Okay, and before going to the spin polarized data on this sample, here I show you that actually on this BISCO 2212 optimally doped sample, we know that it has such a kind of Fermi surface. We have a 7 scattering spots. Okay, and according to the D-wave gap, then we have the 3 scattering with the same side of the gap, 4 scattering with the opposite sign. Then we use so-called phase referenced quasi-particle interference technique. This is a new technique. Then you can clearly show that which one is the scattering between the same side and which one is opposite side. Okay, we found that 3 are having the same sign and 4 have the opposite side. So this is a new technique to show the evidence of D-wave pairing in the cuprate. And this new method avoids the challenge of fabrication, the Jefferson device and the measurement, which is very difficult normally for checking the pairing symmetry. Okay, so this is another story. Let me come back to the ion doped BISCO 2212. So you can see that this is using tungsten measured mapping density state. You can see this kind of block again. And we do the Fourier transform, we see 2 set of spots. One is 4A by 4A. Another one is a 3/4 here, again, on this, even for this sample, okay? This is two typical scattering spot. However, if we use a tunneling spectrum, spin polarized tip, for spin up and spin down, then we subtract these two topography, then you will see that nearby this ion impurity, you see clearly this anti-Fermi order. This the blue and the red shows anti-Fermi order. This is Fourier transform. After subtraction, you can clearly see these spots, which is corresponding to this anti-Fermi order, but it's incommensurate static anti-Fermi order. It is a little bit less than this V vector of the anti-Fermi order in the parent phase, okay, which is about 0.85. For the parent phase, the anti-Fermi order is 1 here, okay? So our theoretical collaborators, Professor Ilya Ermin, did the calculation. They assumed on-site Hubbard U for the repulsive for magnetic state, and the nearest neighbor for the attraction for D-wave superconductivity and a single point like magnetic impurity. They did the calculation, shows this kind of spin polarized contrast pattern, and which you can compare to our experiment, it looks very similar, okay? And also this intensity oscillation, this dispersion also. So it seems that the anti-Fermi order and the antiferromagnetism and the superconductivity, they are very strongly, they are closely interplayed each other, okay? Then I come to the third piece of work, which I will show you the normal state of the BISCO 2201, which has a Planck dissipation. And we found that the ubiquity field is a long Ginsburg line, Landau type, okay? We all know that in cuprate, there were very strange behavior for the so-called BISCO 2201 without the lanthanum doped one. In early time, in 1990, this is a canonic curve, okay? So the near resistivity goes from TC about 7 Kelvin to 700 Kelvin. So that violates so-called phonon scattering. And based on that data, several theorists, especially Jan Zahlen, proposed so-called novel dissipation governed by the many body effect in these correlation systems. So in the entangled compressible quantum metal, and it shows the scattering rate should be linearly versus temperature with this kind of quantum number, okay? The alpha is close to 1. And this phenomenon has been found in many cuprates, and iron-based heavy fermion resonates, okay? And also in this paper, these people collected a lot of transport data and to prove that indeed the alpha is quite close to 1. So that indeed shows such a behavior. And we want to measure more precisely. So we fabricate our single crystal into this bridge, and with a very well-defined size and thickness. Then, and for this sample, it's good that because the TC is quite low, so we can use even the lab magnetic field can suppress superconductivity completely. So this is near optimal doping, and this is the resistivity shows quite close linear behavior. This is for this BISCO 2201 single crystal. By using a 15 Tesla data, the superconductivity is almost suppressed completely, okay, above the temperature of 400 millikelvin. So this is the transition. Then we try to use the Drude model to estimate the scattering rate. But here we have two unknown parameters. One is the effective mass. Another one is the so-called charge carrier density, N. So we use the Hall effect measurement to get the Hall number. And from the Hall resistivity, we determine this charge carrier density. And also from specific heat, we can determine so-called effective mass, okay? We found that the Hall coefficient actually changes slightly with temperature. So we take the average to calculate the charge carrier density, which is gives this value. And also from this specific coefficient, we determine this effective mass, okay? And finally, we get a mass in this value is about 7.33 times of the Bell mass of the electron. And then we use this formula to fit to the resistivity data down to low temperature. We found that the contribution is mainly contributed by a linear term. So here we separate, after the fitting, we use the parameters to calculate the data. So the blue one gives by this quadratic term, and the black one gives by the linear term. So linear term dominate here, okay? So from the linear term and from the mass and from the charge carrier density, we can definitely determine the alpha. We find it's very close to 1, you can see, okay? And actually, some groups say that in the Mercury 1201, they found that if you calculate the so-called Hall angle, which does not depend on the charge carrier density, okay? So in that case, they found that it becomes a linear, so-called Fermi liquid-like quadratic. And we follow the same way in our sample. We found that even we just calculate this 1 over tau by timing this charge carrier density, the temperature dependent, we don't see a linear, we don't see this quadratic temperature dependence. Instead, we see this so-called still rather linear in low temperature region, okay, for this dissipation. So our sample seems different from the Mercury one. And also we determine the upward field by using the Euro weight. So from the transport, 95% of the normal state, we determine the upward field. You can see the data here, which is definitely deviating from the Ginzburg-Landau prediction. The difficulty for this Ginzburg-Landau predicted upward field is that you always have a bending down in the low temperature region. But the cuprate sample shows this kind of divergence. Actually, this behavior has been found in many other systems, such as in Thallium-201 and YBCO by different groups. Then we noticed one paper by Alexandrov et al. Says that for the critical field of uncondensed bosons, which means that this is not real upward field, it is for the condensation temperature and field, it gives some kind of theory, and following the theory, we put forward this kind of empirical relation for the upward field. So this 1 over 1 minus T is given by the dropping down of temperature of superfluid density with temperature, and it gives the T power law in here. So here we assume a small delta here. So we propose this kind of empirical law. We found that the data can be very nicely fitting by this empirical law. So which suggests that we have uncondensed bosons, okay? Here are Cooper pairs, even above the upward field. This boundary just reflect the condensation temperature of field for the electron systems, okay? Actually, in the cuprate, we have been told many times by the so-called local pairing gap and also superfluid density determines the so-called TC DOM. This is given by Emery and Kiverson. And also in the APES data by Donglai Feng et al. They show this kind of coherence peak follows this kind of curve, okay, shows the TC correlation. And also this kind of a cartoon picture says that in the cuprate, we probably have a local strong pairing with a BEC, and when the Cooper pairs the density becomes higher and higher. In that case, we are crossing over to the BCS crossover region. So in that case, I plot this kind of cartoon picture. So in the BCS case, we have the Fermi surface instability due to the weak coupling, like a phonon exchange phonon. And in the cuprate, probably, as I showed by 3 set of data, 3 piece of experiment, that we have a local strong pair due to the correlation, and also the TC is determined by the phase coherence, okay? So here I draw a general camp for superconductivity. So in this big camp, the BCS just sits in the corner, which is due to the so-called weak coupling picture instability of Fermi surface. However, in the cuprate, we have a local pair due to the strong correlation. And in that case, we have some kind of finite density state, and gradually we have superconductivity. So the TC is determined by the superfluid density. And probably the ion-based superconductors is in between this, in this region, corresponding to the BCS to BEC crossover. Okay, so this is my final picture to conclude our data. So then let me come to the conclusion. The first is that is in the underdoped, very underdoped region, we use a spin polarized STM to first time to review that this charge transfer gap will be filled up by density of state in a wide range of energy when the anti-Fermi order is diminished. And the anti-Fermi order is for the first time viewed by the spin polarized STM directly. And at a higher doping, the charge transfer gap is completely filled by DOS. And with a hump in this region, this corresponding to the J value, okay, in the same scale. And meanwhile, some 4A by 4A plaquettes of density state are formed. Within each plaquette, an internal pneumatic state is observed with the peaks of density state at the low energies, okay? And the highest density state peaks appear on the oxygen side, implying that the holes are doped into the oxygen orbitals. And as counting the density, it is tempting to conclude that it seems 2 holes per plaquette. We argue that the local Cooper pairing may exhibit as a confined pneumatic state with a 4A by 4A plaquette. The low energy gap arises either from a pale density wave or the precursor gap for superconductivity. And also, we found the ion-doped BISCO 2212, we found a re-emergent anti-Fermi order with this shorter wave vector, okay, which is incommensurate. And also with the linear transfer data, we found the Plancking dissipation. And also we found ubiquity field, which is not the Ginzburg-Landau type, but it shows uncondensed Cooper pairs above TC. So this again shows, all this data shows that we have strong pairing with variable phase coherence. So this is generally consistent with the picture of superconductivity arising from a doped Mott insulator. So with that, I thank you very much for your attention.
Thank you, Professor Wen. Any
Thank
questions
you.
from the audience?
Yes.
Yes, please.
Thank you for that very nice talk. I have a question about what you showed with the local antiferromagnetism in impurity-doped BISCO. So around some of the impurities, you found the local antiferromagnetism, and then you took a Fourier transform of it. If you could put that slide back up. I had a question about the Fourier transform.
Yes, I try to move to that. Yeah, sorry. So you mean the second part, as ion impurity, huh?
That's right.
Yes. Wait a minute. The web has, wait a minute. Sorry, I come to the second part. Yes. Yes, what's your question, please?
So let's see, there's a slide where you show the Fourier transform of that local you see the local antiferromagnetism, and then you show a Fourier transform of it. Here it
this
is,
one,
this slide right here. So in the lower left, you're seeing, it looks like you're seeing some arcs rather than just peaks. But in the lower left, you see what looks like some arcs. Is that real, or is that just sort of a trick if I'm sitting too far back from the screen?
No, I don't think this is real. So this is you know, it's a Fourier transform of this single spin arc mapping topography. Okay, so this is I think it's due to Fourier transform effect. So it's not, so you can see this spot here, okay, which looks like using a tungsten. And actually, actually, the one quarter one does not show up strongly, but here there was a spot. And you mean this arc, huh?
Yeah, I mean
this
that
one,
arc.
Huh?
I was curious if
no,
you think that's real or
that's
an artifact.
that's not a true effect. I think it's due to the Fourier transform on this picture induced for some reason. Yeah.
Okay, thank you.
Mm-hmm. Thank you.
Any other questions?
Yeah, maybe a comment and a question. First of all, congratulations for these very nice spin polarized STM measurements on the static and the ferromagnetic ordering. Now the question
Yes.
is, do you think that there's a chance also to reveal maybe antiferromagnetic spin fluctuations which might survive even at a level where you do not see the static antiferromagnetic order anymore? So there are new techniques of course available combining spin polarized STM with dynamic processes. So did you think a little bit in this direction?
Well, that's a good question and proposer, but uh, I'm, uh, I must say that I don't have idea how to realize that. You know, spin fluctuation could be very fast. Okay, so our STM measurement is quasi-static. So in that case, probably some short time, time reserved FTM can do such thing. I hope so. But for us, for our technique so far, we cannot do that. Okay. That's a very good suggestion. But we are now, next step, we are trying to using a magnetic field to suppress the superconductivity, then to see whether this magnetic order, static order, or some kind of order will appear again. Yeah, that's is underway. But for the quick fluctuating antiferromagnetism, I don't have the ID so far. Probably some quick measurement, time reserved STM can do. Thank you. Yeah.
Time resolved SPSTM or ESR SPSTM might be valuable tools to look at the.
Yes. That's a good point indeed. Yeah, we need some new technique on the tip. In that case, we can reserve the short time. So that will be very interesting. Yeah. Thank you for the suggestion.
Yes, please.
Thank you very much for the very nice presentation, Professor Hu Wen.
Yes, thank you. Thank you, Professor Genser.
As an organizer, I cannot commit myself to listen to talk, so I may have missed something that you already mentioned, maybe. So
yes,
I'm just going to ask about this iron-based superconductors, thin films.
Yes, yes.
Is it possible to make reproducible monolayers for quantum applications for the iron-based superconductors? I mean, do you have a plan to make this in your laboratory, or is it?
Oh, actually, in China, I think several groups can reproduce this monolayer thin film. Yes, in Tsinghua University and also in other university, now they can produce, like Shanghai Jiao Tong University can produce this monolayer ion selenium film, and the quality looks quite nice. And yes, that's possible. But in my group, we have not tried that direction yet. Yeah, certainly in ion selenium thin film, people try to find the Majorana mode on the vortex core, but it seems on the intercalated ion selenium film, people find such zero mode, but in ion selenium monolayer film, it does not exist. So it could be interesting. Yes, some groups in China, they are growing and reproduce the monolayer thin film. But with magnetization TC, it's about 40 to 50 Kelvin, something like that. Magnetization, yeah, measurement.
I think China is making heavily investment in the field of superconductivity, and this is one of the highlights of the conference. So maybe you can give us some more details if this is available with you.
Oh, if you have time, I can say a few words about that. Yes, indeed, in China, we have quite, how to say, some investment on either fundamental research and also for the application. For the fundamental research, we have the national project from the Ministry of Science and Technology. We have several, I think, maybe less than 10, but something close to 10. Something like how much is 30 million, 30 million yuan, something like that project. And also in the Chinese Academy of Science, we have a much bigger project. For the goal is to fabricate the high temperature superconducting magnet, okay, to use under 20 Tesla for the nuclear physics. I mean, for the fusion tokamak, and also for the high energy physics, for the accelerator. Okay, so that's the big project is running now. So we have either fundamental and application. We have some project, but money is always not enough. So it's I can say it's in a good state. Yes.
What about the big complex in Hefei about quantum technologies research in general, not only superconductivity, maybe?
Oh, that's certainly a big project. That's for the quantum informatics and also quantum computing. Actually, they are also doing the superconducting quantum calculation. So it's a big complex. Not only Hefei. I mean, Hefei certainly Professor Pan's group and team is big, and also it's spanning in whole China. I think it's helping China to explore towards that direction for the quantum informatics and also quantum computing. Both are going parallelly. Yeah. Yes, it's going. Yeah.
Okay.
Okay, thank you.
Yeah.
We think this
Okay.
interactive.
Thank you so much. Yeah.
Thank you.